All right. So, and in our class, I think the last slide, stoichiometric calculations. Yes. Stoichiometric calculations. Let me just open it here. Stoichiometric calculations. Dun, dun. All right. So, Kumar Jonah, Magdalene. Hi, Magdalene. Welcome.
Hello, thank you.
All right. Magdalene. Kitor, I'm going to send you an email before Fetchat class. Ne? When you reply, please reply with your home address. Easy last time with stoichiometric calculations, and stoichiometry is the relationship of the weights or masses of reactants. So how heavy the reactants, so whatever it is you add into your chemical mixture for a reaction, and the weights of the products, whatever you get after the reaction. So we calculate the masses before, during, and after the reaction. And we still apply the same concepts, concentration, molar mass, number of moles, and mass of substance. Ne? So we're gonna continue our conversation again from Yona stoichiometry. Oh no, let's rather wait there, because what I want us to do tonight, is to look at I want to know this quantitative aspects of chemical change. I want us to study how it shows up in grade 11. Ne? So that my devices. Okay. So I also want what you must do. I want you to have, so I want Magdalene to have to tie the concept more grade 11, but for Musa to have some revision. And then later on, Musane, we're gonna do in depth the content as it appears more grade 12. Ne? So I'm just gonna start a new Jamboard. Everyone on a Jamboard, I get. All right, so let's see, chemical change, quantitative aspects of chemical change, page 290. Let's make that 305. All right, so kilometry link to Mtilane. What's this? Jamboard. Yes. You remember last time, Tuesday, Revoletiga standard temperature and pressure, quantitative aspects. Chemical change. All right, so more quantitative aspects of chemical change. The important thing to note is that go grade 10, we just start with the idea at a high level. So we work out based on periodic table. If you are given a certain amount of substance, quantity of substance, then you can work out its molar mass by looking at the periodic table, and then also find the number of moles as well as the mass. And we also went as far as working out the number of moles of water you need to make things into crystals. So now more grade 11, we start off the same concept, ne? Yeah, molar mass, number of moles, and mass. We started off kadi gas, ne? So now gases are another phase of matter. So far we've been dealing with liquids and solids. But gases, it can be carbon dioxide, it can be oxygen that goes into the leaf of a plant for photosynthesis. It can be nitrogen gas, it can be carbon dioxide, it can be any gas really. And when we focus on gases, Moki, Rulela Ranchiga STP. And what STP stands for is standard temperature and pressure. Ne? So I'll just make an example. In some workplaces, even here in South Africa, you'll hear Ranchi when I ask Nobuhle some questions, she'll always mention it's 1 bar, etc. So the pressure that we speak about, standard pressure is 1 bar, and this equals 101.3 kilopascals. Kilopascals are a unit of measuring pressure or stress, and it's the ratio of the amount of force per unit area. That's stress, ne? It's pressure. Its units are Newton per square meter or Pascal. The person who investigated the effect of a force on a surface was Blaise Pascal. We're doing a bit of science here. But Blaise Pascal was a French curious mind, I suppose. And he studied some of the things we know about physics and science and chemistry today. And even engineering, because this we use to work out how the forces in structures affect the materials of the structure, and therefore you need to find the correct material for you can't build a bridge where ka plastic, it'll break if a truck drives over it, but you need concrete and steel which have a stronger material property, and that helps it handle the pressure or the stress. But in any case, this pressure is due to atmosphere. And it's simply, if you look at a square meter of area, 1 meter by 1 meter, and this area is 1 square meter, and you think about a column of air that's above it, anywhere on the planet, a column of air above a 1 meter by 1 meter surface area. When you think about how heavy it weighs, and then you convert that to a weight, which is a force due to acceleration, due to gravity, then that weight becomes this force here. And when you divide it by that area is this area here. That's what gives you the pressure of 1 bar. So in most places on the planet, the pressure of the air on the surface of the ground is assumed to be 101.3 kilopascal or 1 bar. Right? Then temperature, we use multiple scales for temperature. There's Fahrenheit, there's degrees Celsius, and then there's Kelvin. I see how the order of these written like this can be corrupted, but please pardon that. Fahrenheit is used mostly as an imperial unit. South Africa, we use System International or International System of Units. And scientists tend to be very niched because they like the Kelvin scale. So there's a British man who's probably long dead, long gone. His surname was Kelvin. I think he was a lord. He had a title lord. But in this scale, what he developed was that there is absolute zero, and then there is maximum temperature. So on the Kelvin scale, absolute zero is negative 273 degrees Celsius. And I think even more in Fahrenheit, because I think 0 degrees for us is like 30 something degrees for Fahrenheit. So this is Kelvin. This is Celsius. And then Fahrenheit, I'm not sure the conversion at this stage. I didn't memorize it when I was in high school because I didn't see myself going to the US at that time, so I didn't need to remember it. But somewhere we have 0 degrees, and yeah, but the scales are different. So the point is, in physics in this grade, we look at standard temperature and pressure. And this is the assumption that we apply in many of our calculations. And what follows is that when we have our given information, we'll always have pressure at 101.3 kPa. That's our pressure. And then, oh, welcome, Tiamo. Ladies, rejoin like Tiamo tonight, ne? Tiamo is also a grade 12 learner, so Musa, you two are in the same grade, I guess with Nobuch as well. But like I said, my classes tend to build from our foundation of grade 10, adding it to 11 and then 12, so that we can better understand why we learn the things that we learn at each grade. So Tiamo is also joining us. Just welcome him. Maybe when it's warmer, we'll get to meet him in person. But for now, it's cold, so I'm preferring everyone should study at home. So yeah, Tiamo, welcome.
Oh, hi, Tim.
And Magdalene. Yes. Musa and Magdalene, that's Tiamo. Tiamo is a guy, by the way, so I guess I'm the only man in class. So yes.
Yeah.
Right, as I was saying, we normally have pressure, number of moles, and R is what is it? Joules. Okay, we'll discuss what R is. But for now, if we have 1 mole of gas, the gas is not really specified, but we know that its number of moles is 1 mole. At standard temperature and pressure, we can find the volume. I just want to check quickly what R is before I think I also don't remember it quite well. Gas equation. Does anyone know what the R stands for? Gas equation. It's fine if you don't. I'm just going to quickly search it. It's PV equals nRT. All right, so we've got 1 mole, because I don't want to just list these without giving you what the actual name of that is. Yes. We've got R, and we've got temperature. So the formula for ideal gases is typically the pressure times the volume times N, the number of moles. Yes, gas constant. Gas constant. So it's a constant, doesn't change. T is the temperature. And it's usually worked out in Kelvin. N is the number of moles. And P is the pressure in kPa. Volume, standard, we use dm cubed or 1 liter, 1 cubic decimeter. Yes, and the assumption for all those that we are given at all times, so I'll just write those in green to show that here we are good to go. We need to know this off by heart. We need to know this off by heart. We also need to know this off by heart. And yeah, volume and number of moles are pretty much the only ones that we tend to work out. But this is the ideal gas law equation, right? Now, why is it called an ideal gas law equation? It's a general gas equation, and it states the hypothetical idea of a gas. Hypothetical means that we are using a guesswork. We are making a lot of assumptions, and we are just making them based on what's practical and what's known and what has been observed. However, real gases tend to behave a bit different from ideal gases. So I'll just write that down. So real gases behave different than ideal gases. That being said, we won't be doing a lot of, I don't think we'll be doing any real gas calculations here. But I just want us to look at how we can apply this basic knowledge that we have so far so that we can find certain, qualities of, certain chemical reactions for gases. So the types of problems that we tend to have here are finding out the molar gas volume. So let's say we've got one gas that has 1 mole. We're given 1 mole, and we must find the volume. What can we do? We know that our ideal gas equation is the pressure times volume, and that equals the number of moles times the gas constant times the temperature. Unless the temperature is given explicitly as 271 Kelvin or 200 Kelvin or whatever. If it is not given as any other number, we can always assume T, the temperature, to be 273 Kelvin. So now we are having that the number of moles is 1. If the number of moles is 1, then we know the pressure is 101.3 kilopascals. The units are important, so I'll just convert that to Pascal, right? So 101,300 Pascal times the volume, the number of moles, which is 1, the gas constant, 8.31 J K mole, and the temperature is 273 Kelvin. So when we work this out, we can make V the subject of the formula. So we've got 1 times 8.31 times 273, and this is divided by 101,300. So let's just quickly do the math. So it's going to be 8.31 multiplied by 273, I guess multiplied by 1. And then we divide this by 101,300. And it gives us a volume that equals 0.0224 cubic meters. And this is because our pressure, let's just analyze the dimensions. It's 1 mole times joules, Kelvin, mole times Kelvin. So I'll just erase this here. And then this is divided by Newton per square meter. There's a missing dimension. There's a missing dimension. Where could it be? Because these would, okay. The units for joules are, work is force times distance. That is Newton. Yes, okay, cool. So joules, the units for joules are Newton times meters. So then this becomes mole times Nm over K times mole times K. This is divided by Newton square meter. So these are going to divide each other out. They're multiplicative inverses. And we're left with Newton meter over Newton per square meter. And if we have a fraction being divided, where the denominator is a fraction, it's simply the numerator multiply by the inverse of the denominator. And what happens is the newtons are multiplicative inverses and the m's multiply each other and we're left with cubic meters. So now, when dealing with chemical equations or chemical change, our volume is usually in cubic decimeters, or which is 1 liter. And we can simply convert this. The unit of conversion is 123. So to shift from cubic meters to cubic decimeters, we multiply by 1000. So then our volume is 22.4 dm cubed. So that's the first type of calculation we would have. And now this calculation also tells us, if we had any other number of moles for this gas, let's say the number of moles was 3 instead of 1, then what that means is the volume of this gas that we're finding should be 22.4 dm cubed multiplied by the number of moles of that gas. So regardless, the number of moles, we can always find the volume of any gas, regardless of the number of moles, by multiplying like this. So in other words, if we're given 2.3 mole of a gas at STP, as in the following example, so we're given H2 gas at standard temperature and pressure. Standard temperature and pressure is recurring, so keep that in mind. Then if we have 2.3 mole of hydrogen gas at standard temperature and pressure, then the volume of hydrogen gas at standard temperature and pressure would be the 22.4 dm cubed times the number of moles of hydrogen gas. This is simply 22.4 multiplied by 2.3, and then it gives us 51.52 dm cubed. In other words, for us to successfully accommodate 2.3 moles of hydrogen gas in a container, the container needs to be about 51.5 liters big. So if you want to imagine 51 liters, picture 1 liter of long life milk that you can find in the cupboard in your house, and you pack 51 of these, or 51.52. So if you stack them, then you'll get how much 2.3 moles of hydrogen gas is at standard temperature and pressure. Sometimes gases react with each other, and when they react with each other, we'll have to account for the stoichiometry. In fact, I like that we're doing stoichiometry here because in our last class on Tuesday, we ended off with that part of the conversation. And when we ended off with that part of the conversation, allow me to just share. I just want to share Jamboard. So I'm going to share Jamboard, and I'm going to share class from this past Tuesday. I just want to revise. We didn't do any calculations here, but I'm pointing it out because the concept of stoichiometry, which is the relationship of weights between reactants and products before, during, and after reaction, because we did introduce that concept, we're going to go a little bit into it more in working with ideal gases for now, but just bear with me. So when we discussed stoichiometry, we talked about it being the relationship of weights of reactants and products before, during, and after the reaction. So now we're going to do the same type of thinking. We're going to apply it to where? To ideal gases, right? And how do we do that? I'm going to stop sharing. Or maybe I can share this one. Yeah, today. Because if you share it today, then my call doesn't look weird. Yeah. So just how much time have we got left on this call? Okay, so in about 20 minutes, so it's couple my 8:07, we'll just switch to a different link that I'll share because this one is going to expire. All right. Yes, so where was I? So in ideal gases, sometimes the gases react, and if we want to account for the relationship between the weights before, during, and after the reaction, we're going to apply some stoichiometric thinking, which is from from grade 10 stoichiometry, from grade 10 concepts. So we're going to look at stoichiometry concepts in gas laws, so stoichiometry of gases. So in this case, remember we initially started with, if we have the volume of, if we have the number of moles of a gas, then we can multiply that by 22.4 dm cubed to get the volume of the gas at those number of moles. So now if we have two gases, gas A. So we've got gas A and gas B. So the volume here, gas A, will equal the stoichiometric coefficient of gas A divided by the stoichiometric coefficient of gas B, and you multiply that fraction by the volume of gas B. So gas A has a stoichiometric coefficient, how do you pronounce this word? Do you guys know? How to pronounce stoichiometry? You guys know how to pronounce stoichiometry? How to say stoichiometry? All right, so stoichiometry is pronounced. I'll just watch it on here. Let's see. Stoichiometry. No, don't share this tab. Yeah. You know what? We'll find it later. It's fine. I'm just curious how it's pronounced. So anyway, okay. So gas A has got stoichiometric coefficient A, and gas B has stoichiometric coefficient B. Ne? So the ratio of those stoichiometric coefficients is multiplied with one of the, gases. So we're going to apply that to hydrogen gas. Mixing with oxygen gas. And the chemical equation is 2 times hydrogen, which is in gas form, plus 1 oxygen, which is also in gas form, yield 2 water molecules, or water vapor, molecules. So in other words, you've got H2, and you've got oxygenate A, and this gives us H2O that are 2. That's more or less how it would look if you were to zoom in on the particles. All right. Next slide. Yeah. So then we are told that the volume of oxygen is 3 cubic decimeters, because the problem statement is that hydrogen and oxygen react to form water according to the following equation. So we have that equation, it's been balanced. Now after we balance it, we find that we've got these coefficients 1 and 2 on either side. So in other words, we've got 2 moles here, 1 mole, and it gives us 2 moles. All right, so we now given the volume of oxygen. So now if we're given the volume of oxygen as 3 liters, what's the volume of water that is produced? So now we have to use the stoichiometric coefficient calculation. And the first thing we need to identify is how do we label which one is A, which one is B, etc. All right. So since we are only told about oxygen as what we need to focus on in the calculation, I mean, we could be given information about hydrogen, but we're given information about oxygen. So I'm guessing we're going to focus on that. Then we also need to look at these ratios here. These numbers of moles. So the stoichiometric coefficient, which is effectively number of moles from reaction. I'm thinking that's what they mean, but for now, let's just go with that. So the ratio of water to oxygen is 2:1, and the volume of the oxygen is 3 dm cubed. So if we substitute like that, then we simply get 6 dm cubed as the volume of H2O. So I'll just make that, and I'll make this coefficient O2, such that this is going to give us the volume of H2O. All right, so we've got 6 dm cubed as our answer. But how do we interpret this? What does this mean? What it means is that 2 moles of hydrogen react with 1 mole of oxygen, and this gives us 2 moles water, 2 moles of H2O. And it also tells us that 2 volumes of hydrogen need to react with 1 volume of oxygen to give us 2 volumes of water. So in other words, it also kind of makes sense. I mean, let's think about it this way. We've got level on this side, we've got the hydrogen, 2 of those, and this side we've got the oxygen, 1 mole of that. So when we look at just the reaction, when we have to balance it out, in order for us to have the correct number of atoms present in the reaction, we've got 4 hydrogen atoms, we've got 2 oxygen atoms. If we look at the chemical elements, if we look at the reaction or the equation in elemental form, so just looking at the elements. So because we are prompted to have this balance, because if we don't have it balanced, how do we account for the other material? Nature and the universe only know balance. So whatever it is you put out needs to be accounted for some way. It's the whole reason why this thing here, greenhouse gas emissions or the amount of carbon dioxide gas, is a concern, because it's fine if we burn coal via ESCOM to heat up our homes, but after we burn the coal and we get the ash, if we burn 5 kilograms of coal and we only get 500 grams of ash, what happened to the 4.5 kilograms of something else? And what is that something else? then it's the carbon dioxide, and that carbon dioxide is what gets into the atmosphere. So we don't just burn coal and not get anything. We do get something. We will get an environmental consequence. So that's the whole point of looking at chemical reactions from a lens of balance. So if we have 4 hydrogens on this side and 2 oxygens on the left hand side, then we must have the same number of atoms on the right hand side. And if you look at this, then 2 of the water molecules water molecules tells us that it's 2 times 2, and that gives us 4. And if you take 2 times 1, then it gives us the 2. So effectively our chemical reaction is balanced. And we can say that the stoichiometric coefficients are also balancing out. And that's great, because then it means we did everything spot on. So a similar problem to this one, at standard temperature and pressure, what volume of oxygen is needed to complete the combustion of 3.3 liters or cubic decimeters of propane? So it's at STP, we burn propane. Propane is 3 carbons, 8 hydrogens. If you're doing organic chemistry, it will look something like this. So it's 1, 2, 3, 4, 5, 6, 7, 8 hydrogen atoms. And they are close to carbon like that. So Magdalene, when you get to metric, you'll also learn a little bit about this. And so yeah, for this problem, we're told that this reacts with oxygen, and it gives us carbon dioxide and H2O, right? So C3H8 plus O2 gives us CO2 plus H2O. But first, we need to get the correct stoichiometric what's this? Coefficients. Yes, stoichiometric coefficients. So, to get the stoichiometric coefficients, what must we do? We must balance the equation. And how do we balance it? On the left-hand side, we've got 3 carbon. So we must multiply wherever we see carbon by 3. But once we do that, how does it change the number of oxygens? So now we have 6 oxygens. We've got 2 oxygens on the left-hand side, but 6, 7 on the right-hand side. Oh, by the way, this is all gas. This is gas. Yes, these are all gases form. How much time have we got? Oh, hi, Nobuhle. Welcome.
Good evening, everyone.
Yebo. Just heads up, we're joined by Tiamo. Tiamo's also in grade 12, and he's also a guy. So I'm not alone in this fight any longer. So we'll be having class with Tiamo going forward for the next 2 terms. Just a quick heads up, our 5 minutes is almost gonna end. So in like 1 or 2 minutes after we finish balancing this equation, we will just switch to a new link, and then I'll just add you. So quickly, just to balance this equation, so we've balanced out the number of carbons on either side. So carbon, we've got 3 and 3 this side. What about hydrogen? We've got 8 here and only 2 here. So if we multiply the left-hand side by 4, then we'll have 8 hydrogens and 8 hydrogens on either side of the arrow. So the hydrogens balance out. So H is 8 and H is 8. But where does that leave us? We've got 4 oxygens plus 6 oxygens. So 4 oxygens from the water molecule and 6 oxygens from carbon dioxide, but only 2 in the before the reaction takes place. So if we multiply that by 5, then we'll have 10 oxygens and 10 oxygens on either side. So then our equation is balanced. Now that it's balanced, we've got stoichiometric coefficients. So Nobuhle, just before I switch the call, we ended our conversation on stoichiometric concepts. So stoichiometry simply means when we're balancing a reaction like we just did now, we work out the number of moles so that we use that number of moles as a stoichiometric coefficient in the calculations that we need to do for chemical change. So we'll carry on from that point. Just everyone can leave the call and then I'll just send a new link now, shortly. All right, so all right.